Measures of Dispersion, Module 2, Part 3a. Throughout the videos, when you see the stop sign, pause the video and work the problem before continuing. You might want to print the slides so you'll have the data readily available. The objectives we want to cover in this lesson are to compute the range of a variable from raw data, to interpret the standard deviation of a variable, and to use the empirical rule to describe data that are bell-shaped. The range and the standard deviation are both measures of dispersion that tell you how spread out the data is. To order food at a McDonald's restaurant, one must choose from multiple lines, while at Wendy's restaurant, one enters a single line. The following data represent the wait time in minutes in line for a simple random sample of 30 customers at each restaurant during the lunch hour. For each sample, we need to answer the following questions. What was the mean wait time? Which restaurant wait time appears more dispersed? Which line would you prefer to be in, and why? This is the data. You might want to pause and calculate your mean, or you can continue on to the next slide since you know how to do means at this point. The mean wait time in each line is the same, 1.39 minutes. But if you look at the histogram, it's clear that the McDonald's data is more dispersed. Now we want to compute the range of a variable from raw data. The range R of a variable is the difference between the largest data value and the smallest data values. That is, range is equal to largest data value minus smallest data value. You might want to sort the data to more easily determine what the smallest and largest values are. The following data is that same travel data for the web startup company, but now we want to find the range. So we sort the data, and we notice that the smallest value is 5 and the largest is 43. We subtract those two values and find out that the range is 38 minutes. So what that tells us from the shortest commute to the longest commute is a range of 38 minutes. Now let's look at what a standard deviation of a set of data is. The standard deviation is a statistic that tells you how tightly all the various examples are clustered around the mean in a set of data. When the examples are pretty tightly bunched together and the bell-shaped curve is steep, the standard deviation is small. So you would have a steep bell-shaped curve. When the examples are spread apart, the bell-shaped curve is flatter, and that tells you you have a relatively large standard deviation. Computing the value of a standard deviation is complicated, and we're going to let software do that. But we need to understand graphically what a standard deviation represents. One standard deviation away from the mean in either direction on the horizontal axis, which would be the red area in the graph above, accounts for around 68% of the data in this group, or in any group that's normally distributed. Two standard deviations away from the mean, which would be both the red and the green areas, account for roughly 95% of the data. And if you go 3 standard deviations, which are the red, the green, and the blue areas, you have roughly 99% of the data represented. If the curve were flatter and more spread out, the standard deviation would have to be larger in order to account for that same 68% of the data. So that's why the standard deviation can tell you how spread out the examples in a set are from the mean. Why is this useful? Here's an example. If you are comparing test scores for different schools, the standard deviation will tell you how diverse the test scores are for each school. Let's say Cleveland Elementary has a higher mean test score than Bethel Elementary. Your first reaction might be to say that the kids at Cleveland are smarter, but a bigger standard deviation for one school tells you that there are relatively more kids at that school scoring toward one extreme or the other. By asking a few follow-up questions, you might find something like Cleveland's mean was skewed up because the school district sends all of the gifted kids to Cleveland, or that Bethel's scores were dragged down because students who recently have been mainstreamed from special education classes have all been sent to Bethel. Remember, the mean is not resistant. It is affected by extreme scores, so that a higher mean may not indicate that all the kids are generally smarter at Cleveland. It may just mean that you've got a few kids there who drug up the average. Looking at the standard deviation can help point you in the right direction when asking why information is the way it is. The standard deviation can also help you evaluate the worth of all those so-called studies that seem to be released to the press every day. A large standard deviation in a study that claims to show a relationship between eating Twinkies and killing politicians, for example, might tip you off that the study's claims aren't all that trustworthy. Of course, you'll want to seek the advice of a trained statistician whenever you try to evaluate the worth of any scientific research, but if you know at least a little bit about standard deviation going in, that will make your interview much more productive. You can use this site to calculate standard deviations if you don't have a statistical calculator. You enter your data separated by a comma here, and when you hit calculate, it will fill in numbers for all of the results below. You want to use this for your sample standard deviation, and this one if you need a population standard deviation. It will calculate both for you at the same time. It doesn't know whether you're using a sample or a population, so you have to pick the one that applies in your situation. And this is what you'll get if you use a TI 83 or 84 plus calculator. And the sample is the S, and the population standard deviation is the Greek letter sigma. Now see if you can compute the standard deviation for our startup web company data. You should find that the population standard deviation of this data is 11.4 minutes. Now compute the sample standard deviation. And this should just be a matter of reading the other value off your display. That should be 12.3 minutes. It should be no surprise that the population and sample standard deviations are different. Like the mean, the sample standard deviation can be used to give an estimate of the true population standard deviation, since it is rare to have data from an entire population. If you do have data from the whole population, as in some of our small populations in our examples, calculate the population standard deviation. If your data comes from a sample, use the sample standard deviation. Now we're going back to our McDonald's and Wendy's examples. Determine the standard deviation wait time for Wendy's and McDonald's, which is larger and why. Because of the histograms we looked at, we determined McDonald's was more spread out, so we are going to expect that McDonald's has the larger standard deviation. Stop the video after the next slide so that you can calculate the requested standard deviations. You will need to decide whether to use the sample or the population standard deviation. And here's your data again. So since these were samples, we want to use the sample standard deviation, and we find Wendy's sample standard deviation is 0.738 and McDonald's is 1.265 minutes. It is indeed larger, and we expected that because we could tell from the histogram that the McDonald's data was more widely spread. What this tells us is, if we put the mean in the middle of that bell-shaped curve, that the mean of both of them was 1.39. That if we go out one standard deviation above the mean for Wendy's, that gets us to a wait time of 2.128. And if we go to the left one standard deviation, that drops the wait time to 0.652. So what that tells us is that if you go to Wendy's, that 68% of the people that walk into Wendy's during lunch hour are going to expect to wait between 0.652 and 2.128 minutes. If we look at the same thing from McDonald's, the mean is still 1.39. But if we go one standard deviation above the mean for McDonald's, that gets us up to a wait time of 2.655 minutes, or down to a wait time of 0.125 minutes. So 68% of the people, on average, will walk into McDonald's. They're going to wait somewhere between 0.125 minutes and 2.655 minutes. So even though these times aren't all that different, there's less predictability when you go into Wendy's because the data is tighter together. At McDonald's, your wait time could be next to 0, or it could be over 2.5 minutes. So there's more of a spread in what to expect. There's less predictability in how long you might have to wait if you walk into McDonald's. Now we're going to look at the empirical rule to describe data that are bell-shaped, or we call that normally distributed. And the empirical rule is what we've been talking about, that approximately 68% of the data will lie within one standard deviation of the mean, approximately 95% will be within two standard deviations, and approximately 99.7% of the data will lie within 3 standard deviations. It doesn't matter if you're using the population mean or the sample mean. This works as long as your data is normally distributed. And remember that sigma, the Greek letters, are used for population standard deviation, and mu would be your population's mean, x bar is going to be your sample's mean, and s, little s, is going to be your sample standard deviation. So here's what this graph looks like. This is your 68%, but because of the symmetry, if you wanted to just concentrate on one standard deviation above the mean, you could split that 68 in half and get 34%. And if you look at the arithmetic, that's what they've done to get the 13.5% here. If 2 standard deviations is 95%, if you cut that in half, then the half above here would be 47.5%, because that's half of 95. And we know 34% of it is within one standard deviation, so that leaves the 13.5% for this little block here, if you wanted to know how much of your data just fell within that particular range. And you could look at the arithmetic. That's what they've done to calculate all these other values. The 2.35%, 0.15% is what lies above 3 standard deviations. So if you go 3 standard deviations above your mean, you have almost all the data, but there is that tiny possibility that you've got 0.15% that lies up here in these tiny little tails. Here's some more data that represents serum HDL cholesterol of 54 female patients of a family doctor. Compute the population mean and standard deviation. So this must be all of her patients. The video stops after the next slide so that you can perform the calculations. The next slide shows calculator directions and gives a link to a website calculator to assist you. Resume with video module 2, part 3B when you've finished your calculations.